Hello, Mr. Betts here. Let's take another look at an example using implicit differentiation. This is a fairly straightforward problem, but I've got it as a level 2 problem because it introduces a new idea. And that idea is that we can take the derivative of an expression that has more than two variables in it. So we're used to just having x's and y's, but we've got the d in there now. And we can take the derivative with respect to a variable that's not even in the equation. So this gets into the idea of like parametric equations. So a parameter here would be t. Basically, we might have a situation where the value of x depends on what time it is, how much time has passed in a certain problem. The value of y might depend on that also. And the value of d, which this is a version of the distance formula, depends on x and y, which both depend on t. So d would also depend on t. So even though t is not in the problem, we could have values for x and y and d that depend on what time it is or how much time has elapsed in the problem. So the way we're going to do this is no different than what we did before. We identify what we want to take the derivative with respect to, which is t here, and we take the derivative of both sides with respect to t. So mentally, I'm thinking the derivative with respect to t of the left side is equal to the derivative with respect to t of the right side. Now, this is something that I'm just thinking in my head here. You don't have to write it out. But now that we do this, we take the derivative term by term. So the derivative of x squared is 2x. But keep in mind, we're not taking the derivative with respect to x now. So this x is a baby function. And since x depends on t, this is going to be some function of t here. So we multiply by the derivative of x with respect to t. Okay, so again, we're using the chain rule here and taking the derivative of that baby function with respect to this variable. Then we do the same thing for the y. So this is going to look really similar, but it's 2y. And then since the y is the baby function now, we multiply by dy dt. So the derivative of y with respect to t. And then on the right side, 2d dt. Sounds like I have a stutter there, but I don't on this problem at least. And then this is kind of a tricky thing here. This seems like a complicated answer because it has derivatives in it, and it's not actually an answer yet because it says solve for dt. So I do need to get that by itself. So if we get dt by itself, we're going to get 2x dx dt plus 2y dy dt over 2d. And we can actually cancel the 2's. I'm not going to do that. We don't need to worry about that algebraic and arithmetic stuff. But what I want to point out here is that this answer, which is correct and exactly what I was looking for here, it involves some derivatives that were not in the problem to begin with. So if you think about what might be going on here in some application problem, this kind of makes sense. So if x depends on t and y depends on t, so x is changing, y is changing as time passes, then how fast d is changing should depend on how fast x is changing and how fast y is changing. So in an application problem, d dt is the rate of change, I'll call it ROC, of d, okay, which might be a distance with respect to time. Dx dt is how fast or rate of change, so how fast x is changing. And dy dt is how fast y is changing. So we could take this idea of implicit differentiation and apply it to problems that use physics or some other relationship between different variables and look at how fast one variable changes with respect to another variable.